Hello and welcome to episode 47 of Diabetics for Diabetics Radio. I am your host, Bowie Madison. Today's episode is titled Mouse Models in Diabetes, What They Teach Us and What They Don't. And we are taking a closer look at the diabetes research model in mice and how we can take things from mice research and apply them to humans in a responsible way. Whenever I talk on social media about research that I find interesting and it's in the mouse model, I will always get kickback in the comment section claiming that, because I'm not a mouse, what we learned from that paper isn't applicable. And in plenty of conversations I've had with doctors and endocrinologists, when I bring up things that I have read, the doctor is always so quick to dismiss anything pertaining to information found in a mouse model. And it's frustrating because if we are using the mouse model to help inform us on the human diabetic condition, why is it so easy to so quickly dismiss it as not being important if we're using it as a foundation for where human research goes? So I just want to make sure that we are taking the time to appreciate what mouse models can offer us, and at the same time respecting the limitations when it comes to taking what we learned from that mice research and applying it in the human model. So if there's anyone here who has ever been excited about research and had that excitement, slammed in their face because someone told them it didn't mean anything because it was in a mouse, this episode's for you. Okay? So we're going to talk about how they make diabetes in mice and the implications of that when it comes to understanding the timeline of disease development in mice, the timeline of disease development in humans, and some of the possible oversimplifications in the mouse model, how we can take what we learn from those mouse models and actually use it meaningfully in the human model. Without further ado, let's go ahead and get started. So in this episode, we're going to cover a couple different topics outlining the connections between mouse models, human models. We'll talk about some of the shortcomings between them, some things that I do that help me use information from mice research and kind of transpose it over the human system, some of the required understandings that serve as a foundation for those comparisons, because you have to know a little bit more about the human system to take what you're learning from mice systems and make it make sense in human models. So that's what today's episode is going to be focused on. We'll cover each of these points. Let's go ahead and get started with the first one, which is incredibly important from both a mouse and a human perspective, because we really need to know what's happening in the scientific realm of diabetes research, because this is going to give us some insight into what the research community's understanding of how diabetes develops is. So, and I made an episode about this, like how I think it's how diabetes is made in the lab, and it talks about all the things that we're about to rehash. So, two substances you need to be very familiar with when reading diabetes research are alloxan and streptozotocin. Now, streptozotocin came out really clearly twice. I may stumble on that word a couple different times. I may just resort to STZ. Okay, so just from here on out, STZ and streptozotocin are synonymous. Now, these are inflammation-based models because both alloxan and streptozotocin are major ROS instigators that are specific to beta cells. So for the alloxan model, it destroys beta cells by creating a lot of oxidative stress. This is meant to create a model that mimics insulin deficient diabetes because it's basically coming in and it's mowing down beta cells from the inside out. It's just creating so much ROS in a very short period of time that there is an ensuing immune reaction against the beta cells that are dying. Now, I say that this mimics insulin deficient diabetes without autoimmune involvement because this doesn't imply that the immune system has something to do with the loss of beta cells. This is creating inflammation inside the beta cell, and the immune system comes in to clean that up, as opposed to the immune system attacking healthy beta cells and the immune system being the reason that insulin isn't being produced anymore. So here's just a little bit more on the alloxan model. So alloxan primarily induces beta cell death by generating reactive oxygen species. When alloxan enters the beta cell, and you can see here on the right-hand side, it does this through the GLUT2 transporters. So both of these substances basically have very similar keys to glucose. So they get in, they know how to get through the cell membrane without triggering any sort of red alarms. So it enters the beta cell. It quickly undergoes redox cycling, so reduction, oxidation. It's causing a lot of metabolic activity that has ROS and inflammation causing molecules as byproducts, producing large amounts of hydrogen peroxide and superoxide radicals. Those are the ROS. Since beta cells naturally have low antioxidant defenses, specifically low levels of catalase and glutathione peroxidase, they're unable to neutralize these reactive oxygen species effectively. This oxidative stress damages the beta cell membrane, mitochondrial DNA, and other cellular components, ultimately leading to apoptosis or programmed cell death. So, like I mentioned before, it's like a bomb goes off inside the cell by creating all of this RO. Beta cells have inherently low antioxidant capabilities. So it mentioned two specific enzymes, catalase and glutathione peroxidase. Those are two enzymes that are naturally occurring within beta cells, or within cells in lower levels in beta cells, that are used to neutralize and repurpose things like hydrogen peroxide and the superoxide radicals. Okay, those are two forms of ROS. So because the beta cells don't have the tools to neutralize all of this huge influx of inflammation, it dies. And then for the streptozotocin model, this is a less direct ROS inducer. It does this by specifically messing with the DNA of the beta cells. So it comes in, it alkylates DNA in the beta cells, which triggers the DNA repair mechanisms within the cell. Because it does it at such a high level, the DNA within the cell basically becomes a mess. And as a result of the DNA being a mess, it kind of indirectly creates chaos within the beta cell, and it eventually leads to its death. Now, unlike alloxan, streptozotocin primarily induces beta cell death by directly damaging DNA, okay, as opposed to just, creating ROS spontaneously with anything it interacts with within the cell, which is what alloxan does. STZ alkylates DNA, meaning it attaches chemical groups to the DNA strands, which disrupts normal cellular function and triggers a response known as the DNA damage repair pathway. The accumulation of unrepaired damage activates specific polymerases, basically cleanup models, which depletes cellular ATP and NAD+. These are both energy sources within the cell. So basically it exhausts the cell from having to clean up all of this damage. This metabolic depletion combined with oxidative stress caused by streptozotocin byproducts leads to necrosis or apoptosis depending on the dose. Now, I mentioned the dose here. High dose streptozotocin is like you inject it, boom, diabetes happens. That's kind of like alloxan. The bomb goes off, the beta cell crumbles from the inside out. For low dose streptozotocin, it's a little bit by little bit by little bit. So they use the low dose streptozotocin to kind of mimic the progressive onset of diabetes in the human model, right? So it's like a little bit of damage, beta cell struggles to recover, a little bit more damage, the beta cell struggles to recover, a little bit more until eventually full onset. And this is opposite the NOD, non-obese diabetic mouse model. Now, the NOD is a specific strain of mice, a specific lineage of mice meant to mimic the genetic basis of type 1 diabetes development. So these mice are genetically predisposed to develop, basically to have an underdeveloped immune system targeting beta cell antigens. So all of the autoantibodies that we're familiar with as people with type 1 diabetes, GAD65, zinc transporter, insulin autoantibodies, these mice develop these antibodies naturally, or I think around 6 to 8 weeks after birth. And this causes a little bit more along the lines of the autoimmune theory behind type 1. So it's immune-driven beta cell destruction, similar to how we believe it happens in the human model. So this, instead of kind of causing destruction from the inside of the beta cell and then seeing how the body responds outside of it, this is kind of attacking from the outside in, having the immune system be the instigator. So this mimics the immune mechanisms but lacks the environmental complexity. And I added that lacks environmental complexity because, and that's basically what this whole episode is dedicated to, is understanding the context behind the inflammation and what systems go into buffering and managing that inflammation before it actually gets down to the beta cells. I've got a little write-up here about how this happens for NOD. So in NOD mice, the autoimmune attack begins with a failure of immune tolerance. Normally, the thymus, which is a major immune, basically like where our T cells get schooled on what's foreign and what is ourself, right? We need to be able to determine what's us, what's not us, so we don't accidentally attack us. Normally, the thymus eliminates autoreactive T cells, which would attack the body's own tissues. However, in NOD mice, this process is defective, allowing autoreactive T cells specific to beta cells antigens. So this is like very, very manufactured in the sense that the thymus kind of like intentionally doesn't develop the ability to silence autoreactivity against specific antigens for beta cells. So in NOD mice, this thymus process is defective, allowing autoreactive T cells specific to beta cell antigens to survive and enter the bloodstream. These rogue T cells are activated when they encounter beta cell antigens such as insulin and GAD65 presented by antigen presenting cells like dendritic cells and macrophages. So this is kind of like mimicking that autoimmune cascade. So once activated, these autoreactive T cells infiltrate the pancreatic islets. You've got the CD4 plus and the CD8 plus. I talk all about this in outlining how the autoimmune cycle goes. I've got another episode on that as well. And so CD4 are basically recruiting all of these inflammatory markers to come in, fix everything up. The CD8 plus are the killer T cells, so they're coming in and they're actually cleaning up the beta cells. So let that suffice to say, this is the immune system coming in and deactivating the beta cells. So when you're reading research, it's very important to see how whatever claims they're making in the paper work in the specific model of mice, right? So if you're reading research that is focusing on an alloxan or a streptozotocin model of diabetes, you know that it's going to be very, very inflammation oriented, or it's going to act on the immune system, because a lot of the times with that alloxan and streptozotocin model, they kill the beta cells as kind of like, okay, let's just get to diabetes. And then it sees how the body reacts. And then the immune system starts to trigger. And so now viewing how that immune system starts to act on an already dead beta cell, they use research in that regard, as opposed to coming in and already having the immune system be activated in that NOD model. So you've got to know what variables are being manipulated. It's really helpful to know whether or not, if it's inflammation based with the streptozotocin and alloxan, okay, what variables do I need to be paying more attention to, right? You would more likely be focused on ways to modulate the reactive immune system response. With NOD mice, you may be focusing on ways to fortify beta cells against an already existing immune attack. Okay, does that make sense? So just important to know where you're coming from in the research model and how that inflammation is instigated. And some of the limitations of these models beyond just understanding the differences between the two. So the systemic complexity, right? If you're familiar with my content at all, I am a huge believer in the multifactorial origins of human type 1, right? There's a lot that has to go wrong in order for our beta cells to fall victims. This could come from the liver, it could come from the gut, it could come from the nervous system and environmental triggers. It's probably a kind of a perfect storm of all three. So it's very, very hard to replicate that consistently in a mouse model. And that's why when you think of like the NOD or the streptozotocin and alloxan, it's a very short, relatively short timeline. It's kind of like, instead of like, okay, well, let's, feed them this food, let's traumatize them in this specific way, no one's quite sure exactly how all of those factors lead to diabetes. What's used in the research is like very quick. So it's like, I'm going to inject you with this, or I'm going to create a model where the genes automatically make diabetes in this specific amount of time. So it's like, okay, boom, diabetes happens. Now what? And I argue that you really have to consider the systemic matters behind how all of these things develop in order to actually, get to the root cause of it. So really difficult to replicate all of those factors that are going into human diabetes development in the mouse model. In an effort, right, this is all in an effort to kind of simplify the timeline. And this also boils down to lots of modern medicine research being interested in the management of diabetes. They're not particularly invested in finding out how it happens. They just, okay, we've got people with diabetes. What are things we can do to kind of help them along or help manage symptoms, right? Because in that regard, the model that they have set up here is perfect. Because it's like, boom, diabetes, don't need to worry about what's happened. We just kind of needed to knock out the beta cells so that we can figure out what happens in the system afterwards. But as a result of that, there's no like preclinical phase like that's seen in type 1 diabetes from a development standpoint. So from like looking for a cure, looking for root causes, looking for, pre-existing conditions that lead to diabetes, the mice research falls short in that aspect. So it's up to us to kind of piece together those things. So we can see the clear differences in alloxan and streptozotocin-induced diabetes in the mouse model. You've got this inflammatory bomb that kind of explodes in the beta cells and can be useful in seeing how the immune system reacts to a destructive beta cell. You've got the streptozotocin, which is either quickly or slowly, depending on the dose, breaking up the DNA. So similar to alloxan, the beta cell is breaking down, albeit via different mechanisms. So this can kind of slow down or speed up how the beta cell breaks down. This can be even more effective in looking at how the immune system may be reacting on an acute basis versus a chronic basis. And then the NOD model, you have an immune system basically created to destroy the beta cells, and this is giving us great insight when it comes to understanding the autoimmune model in humans, right? You've got the kind of inflammation-based alloxan and streptozotocin, and you've got the kind of immune-initiated destruction of beta cells through that NOD model. Now, taking into mind those limitations of multiple systems at play, obviously we know there's more going on in humans than in mice, especially in this diseased model. Let's start to ask ourselves, okay, now that we know the background of what they're doing to these mice and how the diabetes developed in these mice, can we take what we're learning from these models and actually apply them to humans? So now we've got to ask ourselves the question, with these mouse models and everything they're showing us, do they actually correlate to anything meaningful in type 1 diabetes for humans? Let's talk a little bit more about it. And I alluded to it before in the previous section. There definitely are, but we need to make sure that we are paying attention to the finer details in the human model. So with those inflammation-based models, they're mimicking the inflammatory responses of beta cell destruction and eliciting an immune reaction to try and clean up the beta cell mess. And in that way, it is useful for studying immune targeting therapies, right? Because the general idea is we need a way to prevent the immune system acting on beta cells. Whether that's because there's something wrong with the immune system and it's misidentifying the beta cell, or the beta cell, there's something wrong with the beta cell and the immune system is coming to clean that up. Everyone is so invested in neutralizing the immune reaction for the sake of beta cell survival. Alloxan and streptozotocin, there's the first hiccup, STZ. Alloxan and STZ are both useful because it knocks the beta cells out right away without too much outside or residual noise complicating things, and elicits a very direct immune response in response to the damaged beta cells. And then for the genetic model, the NOD mice, this helps study genetic predisposition because the immune system is the instigator in the beta cell death. So now we can look at some of the finer details as to how the immune system is doing this, ways to disrupt the specific pathways that link the immune system and beta cells. I'm referring to autoantibodies here specifically, and ways to kind of create buffers for the beta cells, whether it be like hiding or neutralizing autoantibodies so that the immune system isn't able to recognize it and preserve the beta cells that way. That's kind of the idea behind the NOD model. But in both cases, both of these models, it doesn't fully replicate the complexity of human development because it's difficult to isolate compounding factors. So here's a quick little grid here. So again, we're operating under the assumption that I have arrived at that human type 1 diabetes is multifactorial. There's a lot of different things at play: genetics, environment, systemic factors, nutrition, you name it. Mouse models are focusing on single factors like inflammation or genetic predisposition. And this is by design, right? Because the research method right now in modern medicine, in order to make claims about what it is you're studying, you have to be able to prove that the results that you observed can be directly tied to the single claim, the single variable that you're paying attention to. And this is very, very difficult to do in the human system because of how many confounding systems are at play. So it's not one-to-one. It's not one-to-one. So with humans and mice, multiple sources of systemic inflammation. We're not really exactly sure how many sources there are, the degree of impact of each of these sources, right? Like is liver damage more influential in beta cell destruction, or is gut health more destructive in beta cell, for beta cell health? Not sure. Is there an interplay between the liver and the gut? It's just infinite ways to go about it. Mice, very targeted, right? Alloxan, STZ, and the NOD model are all like, okay, boom, beta cells. With a flip of a switch, they're gone. With minimal residual tissue damage, right? It's very like, okay, well, diabetes happens. Let's focus after the point. Whereas what I'm interested in is, okay, well, what was going on beforehand leading up to this beta cell destruction? So we'll talk about this a little bit later on too. Mice have a greater capacity for new beta cells. They just have higher rates of beta cell regeneration, and it could come down to the system-wide aspect of things, but we'll get there as well. And then just the controlled environment. When you're studying human models of diabetes, there's just so many confounding factors, right? Like, what was their childhood like? What social, what environmental, what nutritional things are going into this. It's impossible to control for all of these things because no two people were raised on the exact same food, the same feeding schedule, the same, toxin exposure. It goes on and on. Whereas opposed to these mice, it's fairly consistent, fairly traceable. And again, which allows for clearer results in a research perspective, but when it comes to actually applying it in real life, it gets more complicated. And here's my general take, and just an example of this. Mice models allow for a general idea of the downstream impacts of isolated variables, right? Key word here is isolated. They have to be able to take something, connect it to something else, and definitively say that it was that and only that caused the difference. So, does taking this particular substance help or hurt this aspect of beta cell health in a diabetic state or, insulin producing, non-insulin producing state? What we have to do is we have to be able to take these variables, whatever aspect, whether it be the substance or the tissue or the characteristic within the diabetic system, and transpose them, overlay them with the more complex human system. So in that regard, we need to know more about what human systems we need to be paying attention to make sure that we're covering our tracks whenever we are starting some kind of treatment or substance or, intervention. All right, so we've noted the key differences, right? There are obviously more systems at play in the human model, from a gut, a liver, an immune system, the speed of progression of the disease itself, a nervous system factor. It's very difficult to replicate those things in a mouse model. But moving forward now, let's really take inventory of what we need to be paying attention to from a variable perspective if we were to transpose those mouse models onto the human models, right? So with the topics that we are focusing on in mice research, when we look at it through the lens of the human, what actually are those systems that we need to be paying attention to, and what are the nitty-gritty details within them that are going to help us get the most out of those mouse models? So here we have this neat little Venn diagram here looking at the wide array of combinations of factors that go into human type 1 diabetes. And so when using the results of mice research and using them in a human model, we need to make sure that we're respecting all of the complex factors, the overlaying factors that go into the systems that are affected in the development of diabetes. And I focus a lot on the liver, the gut, the nervous system, and nutrition as main means of creating basically like a foundation of health for cellular health in beta cells. And just from an immune standpoint, both the liver and the gut serve as critical buffers in handling toxins and inflammation, ROS. Like, these things need to be operating at a high level in order to protect beta cells downstream. So liver and the pancreas connection is undeniable, right? Even in a healthy system, they are talking constantly. The glucagon, the insulin, glycogen release from the liver, those are the two organs that work together to help keep blood sugar stable in a healthy system. And when you look at some of these paper titles here, elevated iron indices in patients with diabetes, that first one specifically correlates to the liver just because the liver is the site of iron recycling. That's one of my major focuses is iron recycling, the health of the liver being a determinant for beta cell vulnerability downstream of the toxins and inflammation that results from a compromised liver. So a healthy liver is crucial in glucose regulation, and it is often affected early on in type 1 diabetes development. Not sure exactly of the timeline, like how quickly is the liver compromised? How long does it take for the liver to be compromised and get worse in order for the beta cells to be affected? Is it the beta cells first and then the liver goes? I really don't think so, but you get the drift. And then for gut health is in every conversation around health these days, especially in the autoimmune community, but it does have very specific ties to type 1 as well. And you can see that second title, role of gut microbiome in beta cell and adipose tissue crosstalk. And the last one, GABA promotes human beta cell proliferation and modulates glucose homeostasis. GABA being a neurotransmitter that is released by beta cells, but it is also sourced from the gut microbiome as well, right? So the gut microbiota is a major player in both like a chemical signaling pathway with GABA, but also like GLP-1 production, glucagon-like peptide 1, which is a major player in blood sugar regulation in beta cell health specifically. It's all sourced from the gut. So gut microbiome imbalances, intestinal permeability that results from advanced inflammation in the gut have definite roles as possibilities in triggering autoimmunity. I have to be careful how I word that. And then environmental triggers like diet, pathogens, and how they can influence gut health, right? So like how is the quality of the food we're eating impact our gut health? And as a result of that impacted gut health, how is that influencing our beta cells? And that we mentioned that here. You just look at these first two titles on the right-hand side. Evaluation and effect of macronutrient combination on blood sugar levels, right? Just from a sheer fats, proteins, and carbs, how is this impacting our ability to stabilize blood sugars? And then secondly, from a micronutrient standpoint, how are the roles of minerals and trace elements in diabetes and insulin resistance? So there's an undeniable tie to our nutritional input on how we regulate our blood sugar. And then viruses, right? Coxsackie virus, the hand, foot, mouth disease. This tends to have the most direct impact on beta cells, according to the research. But you get into Epstein-Barr, you get into herpes simplex. I forget, HSV, herpes simple complex. I forget the name of it, but there's a lot that goes in. And the mouse models, it's nearly impossible to apply these multiple variables, right? Like, can you imagine a mouse study where you have a high volume of mice who have altered livers, who have altered gut microbiomes, who are exposed to viruses, and who are in nutritional deficits, right? All of these compounding things. It would be an absolute nightmare from a research perspective because it would be so hard to replicate that over and over and over again. So, things to keep in mind when you're reading. And then this, taking into account all of those multifactorial factors going into type 1 development, you have to question the timeline and how significant that is in understanding what goes into type 1 developing. So a hypothetical human timeline up top, and you see on the timeline itself, how long does it take for type 1 to develop? No one even knows, right? Some people have a better idea of it now because of the appearance of the autoantibodies. But even then, the autoantibody tests are rarely used preventatively. They're usually like, something seems like it's up from a blood sugar standpoint, from an energy standpoint. Let's check the autoantibodies. And if they test positive for that, even if they aren't technically diabetic, they are basically fast-tracked for it. But we really still don't have any idea how long those autoantibodies have been around and the factors that cause them to come about in the first place. So, hypothetical timeline. Now, you see I have the liver here, I have the gut here, and I have the nervous system here. These three are interchangeable in terms of their impact, right? The nervous system could be first, the liver could be last, the gut anywhere in between. But these are all the things that are going on over however long. It could be 1 year, it could be 5 years, it could be a few months, it could be a few weeks. No one's quite sure. But you have to think all of these things are developing over time. The body is constantly adjusting to these changing factors. And with each of these adjustments comes a new metabolic profile, comes a new immune signaling cascade. You know, it's always changing. It's never the same as the conditions deteriorate and the beta cells come more and more under fire. So there's a lot of different factors to consider. Disrupted cellular mechanisms, progressive beta cell loss, long-term metabolic shifts, right? There's a lot, the longer that timeline gets, the more complicated understanding and retracing the exact steps of what happened and all the adjustments that were made gets. And this is compared to the mice timeline here at the bottom. And this is near instantaneous. And again, you have to keep in mind that a lot of diabetes research is interested in managing diabetes after it's already there without too much of concern about how it got there in the first place. It's like, how do we create diabetes so that we can focus on the diabetic condition, as opposed to how do we retrace how diabetes came about in the first place, right? So chemical induction, alloxan, streptozotocin, depending on the doses of those, diabetes is like a few days, right? Those beta cells are targeted, the immune system comes in, everything's dead. The gene malfunction, which is the NOD model, okay, the immune system comes in, knocks everything out. This happens over a course of several weeks. You have that targeted inflammation to beta cells. Boom, you've got diabetes, and then you can study, what happens after the fact. But this mice timeline is much shorter, much fewer variables than the human one. And when you consider this timeline, let's just take one kind of benign substance here and see how we can apply that in a human model. So let's say a mouse study comes out and says that turmeric can decrease inflammation. Let's say it decreases specific inflammatory markers, and this leads to improved insulin sensitivity. So they have diabetic mice that take turmeric, and their fasting blood glucose improves. Okay? People will read that title and they'll say, amazing, I'll take turmeric and I'm good to go on I'll need less insulin, or if you're type 2, I'll have better insulin sensitivity. And I'll say, considering turmeric, okay, we need to think about what are the human variables over on this left-hand side. What are the human variables with possible diabetes impacts, right? So
Okay, turmeric decreases inflammation, improves insulin sensitivity. Is this a result of its impact on the gut? Is this a result of its impact on pathogens? Is it helping our liver? Is it, stabilizing our nervous system? Because there's a lot of different ways to influence insulin sensitivity. So, from a research standpoint, or from like a personal, I want to try turmeric, I wonder how it's doing what it's doing, or what components of my life I need to be paying attention to. Is it decreasing gut inflammation? When I take turmeric, how are my bowel movements? How am I processing food? What are my post-meal blood sugars like? Does it target liver issues or liver tissues? Does it get rid of pathogens? Am I passing parasites? Is it kind of keeping entrenched viruses in latent phases? And then from a compounding aspect, okay, let's say turmeric is really good for my gut and my gut is less inflamed. How does this change my nervous system, right? If my gut is less inflamed, I'm absorbing more nutrients. The more nutrients I absorb, the more well-nourished my liver tissues are. There's so many ways for these things to overlap and influence the other variables. You really have to pay attention to the what, the why, the how, and the what else it's doing. And on the opposite side of things, and I'm coming at this from kind of like a modern medicine standpoint, just because something is being lauded for being good for one variable in the diabetic condition, that does not mean that it is good for the diabetic system as a whole. Okay? So something that is good for one aspect of diabetes, let's say something that takes care of the liver, you could say metformin. Metformin has been used forever in diabetes. It's good because it stops the glycogen release from beta cells and keeps blood sugars from going too high on its own. But if this is coming at the expense of our gut health and causing a greater imbalance of gut microbiome, that's not good, right? That's kind of in helping one variable that impacts diabetes, it's making another variable that impacts diabetes worse. And we're looking for net positives here. And in a lot of the stuff that's being pushed out now, it really seems like we're taking one step forward and 3 steps back. So modern medicine loves it because they've made an absolute fortune treating independent variables without any sight for the system as a whole, right? Sure, yeah, we'll get your A1C down, but you're gonna need new kidneys in a couple years. We'll handle that when you get there. It's like no. We want to improve the quality of the system as a whole. So like Glucerna shakes, all of the the shit nutrients in it, the polyunsaturated fatty acids, the preservatives, the dyes, the artificial flavors. Blech. So being immediately good for blood sugars doesn't guarantee it's good for the systems responsible for establishing blood sugar control. Don't lose sight of the forest for the trees. Yes, you may be able to drink a Glucerna shake and your blood sugar will be stable, but you are demolishing your body's ability to actually absorb real nutrients when it is that you come to eating real food. So in that regard, it's not worth it.
So clearly there's a lot of balls in the air when it comes to getting a true understanding of the foundation of type 1 diabetes in humans. So it's just so difficult to replicate that precisely in a mouse model. But let's take a closer look now at what that means, what that simplified version in the mouse model means exactly for how we look at the human model.
So what this all boils down to is that it really seems that the mouse models oversimplify the development of diabetes, the timeline that goes into all of the things that make diabetes happen. They're useful in understanding the body's reaction to the loss of beta cells. But from what it learns in that regard, you still need to consider the confounding systems that went into the development before the research came into question, right? So things to keep in mind here. Mice research, the focus is on the pancreas and the beta cells. The inflammatory and genetic initiators are beta cell only. That's it. Come in, destroy the beta cells. We'll focus how the system adjusts after the fact. Doesn't consider any of the upstream effects, liver, gut, nervous system regulation that precede type 1 diagnoses. And I mean, this goes so much further than that, right? Cardiovascular, neurological, immune system factors that are both upstream and downstream of diabetes management, right? So like, let's say you have some sort of cardiovascular issue, right? It could be an oxygen flow, hypoxia. A lot of people with type 1 diabetes experience hypoxia to some degree. So you have hypoxia, you have poor oxygen circulation. This could be tied to iron and hemoglobin, but okay, so you have that issue. That's a cardiovascular issue. Type 1 diabetes develops. You have an inability to regulate your blood sugar. Elevated blood sugar leads to a much higher instance of cardiovascular disease. So you had a pre-existing issue in the cardiovascular system, diabetes develops, and now a new facet of that same affected system emerges. So now you've got multiple variables within the same system to pay attention to. And there are neurological components to this. There are immunological systems to think about in that regard as well. And then unrealistic timelines. And I have this syringe here, right? Because it's like alloxan and streptozotocin inject, boom, diabetes. So mice are developing diabetes rapidly within days to weeks. We're unsure of the exact timeline for humans. If it's years long, that means our body is in a years long adjustment period. Things are changing, right? It's not just like one day you can process glucose, the next day you can't. You've been losing little bits of it over a very long period of time. And this difference limits the study of early interventions in mice because there is no early development of diabetes. It's boom, diabetes or no diabetes. And then, of course, the immune factor, right? Mice in the alloxan and streptozotocin-induced diabetes don't have the same immune profile as those in the NOD or the human model. So this is important for people looking at numerous research studies, right? So you could have the same, like turmeric, again, just from what we referenced before, turmeric's impacts in the alloxan and STZ-induced diabetes model might have different impacts in the NOD diabetic model. It's got different things to pay attention to. And then with the lack of systemic impacts in the mouse model, combined with the fact that mice regenerate beta cells, which we're going to cover in the next section, faster than humans, might some of the regeneration talked about in the recent, like, okay, if you take turmeric, oh my God, beta cells regrow in this mouse model. If they don't have that same compromised immune system or the same deficits in the other confounding systems, right? Like if their liver isn't messed up, if their gut's not messed up, maybe healing those damaged beta cells is just a simple wound repair mechanism, and it's really not more extensive than that, which is why beta cell regeneration has been so elusive in the human model, because we have to take into account all of those different confounding factors.
So there's a little look at the differences in the logistics of mice and human models. Again, I don't want to discourage anyone from taking important things from mice research, but you have to know it. Now, that's the logistics side of things. There is more to look at in a different standpoint biologically. So I know when I was first diagnosed in 2001, stem cells were new on the scene, and the push for those was all rooted in the idea that human beta cells just don't regenerate, and once you lose them, they're gone for good. And it's worth looking now at some of the inherent differences at the rates of mice beta cell regeneration and human beta cell regeneration to give us a little bit more context in understanding some of the results seen in mice research and how that might differ a little bit when using it in a human model.
So now let's talk about some of the differences between beta cell regeneration in mice and humans, getting down to the specifics of it. So I've got this nifty, get myself out of the way here, get this nifty little graph here. This is an AI generated comparison of regeneration rates for beta cells in mice and humans, both youth and adult. So mice have higher beta cell regenerative capacity, especially when they're young, right? Even humans, young humans, have greater abilities to regenerate beta cells. There's this period, I think, when they're sometime between 1 year old and 3 years old, where beta cells boom. They boom, they're weaned off their mother, they're introduced to outside glucose sources, and beta cells really flourish. But then after that, after they've kind of grown that reservoir of beta cells and insulin production is, the capacity for insulin production is very great, regeneration rates go right back down. And you know, when there are injuries introduced, like beta cells taken away or messed with, the human beta cells regenerate much more slowly than adult. It's slower and much less consistent, right? And these percentage rates are all like relative to one another. It's all AI generated, but it is based off of multiple research papers. So this isn't just nonsense. It's based off of research, but it's not something I want you to go home and be like, okay, well, if I'm at 10% of 80, 10% of 80% that the mice are experiencing, and try to do some sort of like weird math in your head. Don't do that. This is just kind of for visual sake. Where do we stand in comparison to the mice models, and how quickly they naturally regenerate beta cells compared to us? So from a mice standpoint, more targeted inflammation specific to the beta cells, less, and as a result of that, less residual systemic damage, fewer variables to control, as well as a greater inherent capacity for regeneration. Now, that doesn't mean that humans don't have a pretty cool regenerative capacity. And I've got this awesome graphic here, which I talk about and reference a lot in the previous episode, episode 46, The Secret Life of Beta Cells. But humans retain beta cell regenerative potential even in long-term type 1 diabetes. There are multiple studies, multiple videos on YouTube talking about how people who have had type 1 diabetes for 30, 40, 50 plus years continue to show new beta cell growth. Now, obviously, there are many different things that influence the rate of that growth, how old you are, right? The older you get, the slower that rate of regeneration gets. How much inflammation are you undergoing? What is the degree of the immune kind of neutralizing the net negative immune impacts, right? So even if you are able to regenerate beta cells, if your immune system is knocking most of them down after they're regenerated, it doesn't do you any good. So there's a lot of research focusing on enhancing the regeneration through multiple therapies. This could be the GLP-1 agonists combined with Harmine. It could be stem cells. It could be protected stem cells to prevent the immune system acting on those beta cells. But I don't want you to think that human beta cells are just kind of like a wet rag and aren't able to do pretty cool things. But you need to consider that we haven't nailed down all of the exact sources of inflammation. We still don't even know if beta cells are a specific target of something, like what's implied in autoimmunity, the rogue immune system attacking the beta cells specifically, or if the beta cells are just passive victims to systemic inflammation, in which case we would need to be paying attention to the pre-existing systemic damage and the implications of that on the multiple systems impacting glucose regulation. And when it comes to a research standpoint, it's difficult to view those variables in isolation because they can't be isolated. Their true impacts have to be seen in the context of the whole. They can't be isolated. And that may be what leads to that lower inherent capacity for regeneration, because you really have to, there are a lot more T's to cross, a lot more I's to dot when it comes to making sure that beta cells have what they need to regrow.
So while there are major differences in the rates of beta cell regeneration in mice and humans, I do not want that to discourage us from the fact that human beta cells have a huge potential for regeneration given the right environmental conditions. And we talked a lot about this in episode 46, what those environmental conditions are to help beta cells along. But let this serve as a starting point for seeing results in mice beta cell regeneration efforts, taking into account all of the other variables that we're seeing in the human condition, and then using that and laying that out with our greater understanding of the human condition. It's not one-to-one, but it can still inform and make for better decisions in the human model. So let's go ahead and head to the episode summary. That way we can rehash everything and make sure that we've got all our ducks in a row.
So with all that said, mouse models are invaluable for understanding isolated mechanisms of the type 1 diabetes system, but they don't fully replicate the complexity that goes into human diabetes. And I'm dying on this hill. Human type 1 diabetes involves multiple systems: liver, gut, nervous systems, immune systems. All of these things are intertwined. They are inseparable. And from a research standpoint, they cannot be separated and isolated. They work together. So when it comes to the mouse model, which tends to be more isolated from a variable standpoint, from an inflammation standpoint, from the systems affected standpoint, we need to be cautious when interpreting these findings especially when it relates to regeneration and the timeline of disease progression, because there's a huge difference between the human model and the mouse model. And with that, I can't thank you enough for being here. Okay, so this is episode 47. I can't believe it. We're coming up on 50. We're coming up on 50 episodes. I'm really excited about that. Let's keep this conversation going. So take what you've learned here and apply it in the research that you're reading, and see how that changes how you're taking in that information and impacts how you take what you've learned and how you apply it to yourself, and some of the different variables that you're paying attention to in your own system. So don't hesitate to leave questions or comments in the comment section. Make sure, if you know someone with type 1 or are responsible for someone in your life with type 1, share this episode. Share what you're learning. Everything about this gets easier when we start to talk about it. We got to talk about it, okay? And if you're interested in more, you want to look back on some of the stuff that I've referenced within this episode, in other episodes, subscribe. Subscribe to the channel. Check me out on TikTok at Bowie_Madison, or search Diabetics for Diabetics. I'll be there. And with that, this is episode 46. No, this is not episode 46. This is episode 47 of Diabetics for Diabetics Radio. I can't thank you enough for being here. Cheers, and enjoy the rest of your day.